a short recap of what we were doing yesterday. So we are on this first topic of classical aspects of AdS₃ gravity. And we were looking at this theory of pure AdS₃ gravity. And what was the main feature of this theory? Okay, here's some mumbling. Right, and that implied that there's no local degrees of freedom. So this is a theory with no local degrees of freedom. So no gravitational waves. Still, there was an interesting, there's a non-trivial phase space. And we constructed this phase space by imposing first boundary conditions. So our boundary conditions were this. Then we looked at the diffeos that preserve those boundary conditions, and roughly speaking, these diffeos I'm not going to write the whole expression again, but just to give you a feeling. Plus ... And then third, we looked at the reason why this has a non-trivial, this describes a non-trivial phase space, the set of diffeomorphism, is because there's charges associated to each of them. Sorry. Charges Q that will depend on the zeta plus and zeta minus, and the expressions that we got for these charges. So I'll write them in this way now. And the bar, fill in the blanks. And the nice feature of this thing here was that there was this Virasoro algebra L over 8G. Okay. So that's what that's a short recap of what we did the last lecture. Now, also the charges, maybe let me just write one last thing. We also described these charges in terms of the stress tensor, which evaluated to this. So something that will be useful today that I'll generalize a little bit. Sorry, this was plus ... asymptotically. So I'm taking here the limit as r goes to infinity. Something that I'll write here today, you can check this at home, or maybe it will be already natural for many of you. So here I picked the metric to be the flats. So this is what we were calling this boundary metric, this two-dimensional, this gamma ij. It's a flat space. It's just Minkowski. This portion of the metric. You can generalize this discussion to write here any gi j that just depends where I and j are basically running through t and phi. Okay, so you can put any metric that you want here. And what will happen is that in terms of the stress tensor, there will be a generalization to this for arbitrary curve backgrounds. And what you will find is that the stress tensor is determined by the fact that it has to be conserved, and its trace is given by this, where R2 is the curvature. So this is the Ricci of G0, and C is 3L over 2G. Okay? In our case, there's no curvature on the boundary metric. And then conservation basically tells you that you have a holomorphic and anti-holomorphic component of the stress tensor. So that's why it's the same statement. But if you generalize it to any curved background, G0, then you will get that, okay? So we'll use that in a little bit. But okay, now, what are we going to do now? So now we're going to look, so this was the perturbative part of the spectrum, because these are infinitesimal diffeomorphisms, so there's a small parameter describing them. That's why I call them perturbative. And in general, these type of solutions, so this type of diffeo, so we call them large because they have a charge associated to them, but they're described by this infinitesimal parameter zeta, but zeta plus minus are infinitesimal parameters, infinitesimal functions. And for this reason, these things are usually in the jargon of AdS CFT. This is what, or well, in the jargon of 3D gravity, this is what are called the boundary gravitons. Well, this color is not very different from white, but okay, which are the perturbative solutions, perturbative part of the spectrum. Okay? So now we're going to move into, thank you, big yellow, more yellow. Okay, but there's also yellow there. Okay, great. So now we're going to move into, I also mentioned last lecture that there were non-perturbative solutions. And the solution that I want to present to you, it's what's called, there's many of them. I'm not going to describe for you all of them, but the one that is very famous and the one that will be useful for what we're going to do and what comes along will be on what's called the BT-set solution of AdS₃ gravity, okay? So let's write down, I'll write down for you a metric, a line element, and what will happen during the next hour is that we're going to try to understand properties of that line element, okay? And why am I calling it non-perturbative? What are the properties of it? And how does it tie also with this other discussion? We'll also put it in the context of this discussion that we had here, okay? So what is the line element of BT set? So, yeah, I think I'm just, I always debate how to write it, but I think I'm going to, yeah, I'll write it the way that I like to write it. dt squared plus r squared d phi, and then here minus r plus r minus divided by r squared dt squared, okay? So this is a three-dimensional line element where r plus and r minus are constant, and L is again just the, well, it's the AdS radius that we had before. And let's study this line element. Okay? So what are properties of this line element? So the first property, most important, is that this line element is a solution to the equations of motion. Okay, so you can plug it in, Mathematica, you can do it by hand. In the problem sheet, it's like the first thing that I ask you, check that this thing is a solution to the equations of motions, and it is. Okay, so we'll have like all the properties that we'll have that R was equal to 6 times lambda, and R mu nu is equal to 2 times lambda G mu nu. Okay? So it's a solution of our equations of motions. First statement. Okay. Second statement, though, let's see. What is a second thing that we can say? A second thing that we can say, yeah, let's start here, is that this solution, so it has these two constants here, R plus and R minus. And so if you look at it, you might worry what happens to the solution if you're close to, let's say, R equal to R plus. Okay? Oh, and I should have said here, we have R plus and R minus constants, and phi is identified with 2 pi. Okay? But the way that I wrote this metric using this coordinate, something that might worry you is like, it looks kind of funny. It'll define like the same way that Chiara was pointing out in the black hole solutions that she was studying. It looks like there's something funny going on around R equal to R plus. So basically the question is what's happening around R equal to R plus. And I should say here, I'm calling them one plus and minus because without loss of generality, I'm going to assume that one is bigger than the other one, okay? So there's just two constants and you can just decide that one is bigger than the other constant, okay? You can ask me later, well, Chiara will tell you all about when those two constants are the same. I'll leave them just with that hierarchy for now, okay? The boundary metric. So if you generalize this to a general boundary metric, then that's R2 is the curvature of that two. Yeah. So I call it 2 because it's the two-dimensional curvature. It's not the three-dimensional curvature. Okay. So what you can do, so in this case, we can do a coordinate transformation. So consider this coordinate transformation implemented on the BT set. And this is the line element that you're going to get. Let's now do something. So this starts ringing a bell, or not? Does it look similar to something that I wrote before? Almost, right? So what was the metric? Let's write it because I'll use it. So I wrote last lecture the metric of global AdS₃. What was the metric of global AdS₃ written in this Koch row thing? Go back to your lecture notes. Dictate it to me. Minus what? Let's call this one, since I'm using phi now for BT set, let me call this d phi squared, right? And there was an overall factor of L squared in front. Okay? So that was global AdS. Now let's go to Euclidean. So let's take T to Euclidean, and I'll also do it here. So let's take T to IT Euclidean. So the Euclidean metric is this. So what would we conclude if I focus on these Euclidean line elements? They're basically locally, they're the same line element. Right, so let's, so now I'm in Euclidean signature. This line element is basically the same as what that one, but without having said anything about identifications, right? But these two line elements, if you forget about like what is an angle and what was time, I mean Euclidean signature, so these two directions are spatial. They're exactly the same line element, okay? So locally, I have the same space. What is this telling me? That what I told you at the beginning, that all solutions are locally AdS₃, basically I'm just showing you that. I wrote something super fancy here with our pluses and our minus, but I just constructed for you a diffeomorphism that made it basically locally the same as AdS₃. Okay? But we're still giving the solution a name. We call it BT set. Why are we not calling it global AdS₃? So let's see, why are we not calling this line element global AdS₃? Because locally, it's exactly the same line element. Okay, so when you look at this solution here, so we said these things are solid. So in this case, we said this was a solid cylinder where this direction was, sorry, now I'm using this notation var phi. So this was var phi, right? And from the Euclidean point of view, well, also from the Lorentzian if you want, but let's do this analysis in the Euclidean. The reason why phi is periodic is because this direction, so rho here is 0, and then it goes to the boundary to infinity. But basically, phi is periodic because of a regularity condition at the interior of the solid cylinder, right? You don't want to have a cone when you go to rho equal to 0. So phi has periodicity 2 pi due to regularity at rho equal to 0. Right? We agree? Yes. Okay, so now let's look at this line element. What would we conclude here? So I have for you this line element. If I take rho equal to 0, what would be the statement of what has to be periodic with 2 pi? TE, right? So in this, from this point of view, I have a solid cylinder. Again, you would have told me this should have been something like a solid cylinder, where TE has to be periodic and with period 2 pi. Now, in this case, we came from this solution, right? So we came from like the solution that had R, T, and phi. And demanding that the Euclidean time is periodic is clearly not the same as saying that this angle phi is periodic. Right? Because if I make phi periodic here, it doesn't like, it's nothing to do with TE. So let's track what are the implications of these two different regularity conditions. Okay? So this regularity condition is basically the same one when Chiara was showing to you how you had Rindler space and she was constructing the surface gravity. I'm basically doing the same thing. This is that in this case, I have the luxury of constructing for you exactly the coordinate system that takes you to this like Rindler patch. And so this is my regularity condition on the Euclidean time. And if I track it back, so here, I know this box is very important. So now by looking at this map, I can see what are the implications of basically my identifications. So let's do that carefully because that's going to be important. Let's see, what do I want to erase? Yeah, now let's erase this. So for BT set, what we have, okay, so let's write down again what we have. So we have that yellow box equation. So we have that T hat is equal to, I wrote R plus over T over L minus R minus times phi, and then capital phi equal to R minus T over L minus R plus times phi. And we have that this Euclidean time, sorry, did I put a hat in the thingy there? No, I forgot to put a hat. This Euclidean time is periodic, and we have that phi is periodic. Okay? So the fact that this time is periodic with 2 pi, you can translate it back to a statement here, because you can just see, basically, if you want, you can reverse the coordinate transformation, do it however you wish, like you can write it in reverse. But what you can see from here is that what this implies, and this, what this identification implies in the original coordinates t and phi, is that it will tell me that the Euclidean time t and phi will be periodic. So I wrote it. We'll have those identifications where beta and theta is something that we're going to call one over beta. Okay, so demanding that this time, yes. Yeah, did I make a mistake? Ah, sorry, there's a minus sign, I guess. Okay, okay, good. Yeah, so this identification basically implies that you have this identification of 2 pi that is telling me that the Euclidean geometry that I wrote there in that big yellow box tells me that in terms of the original coordinates that I have there, there's an identification of the coordinates in terms of this beta and theta. And then this identification here, the fact that phi goes to this periodicity 2 pi, it actually tells me, so you can, so yeah. Well, let's put it, maybe let me put it this way. Well, you of course can reverse it. But basically, if you see like, what does the identification of phi to 2 pi tell you about these coordinates here, it basically will tell you that each of these 2 coordinates now will transform, right? And so there's different ways how to write it, but one way that is convenient how to write it, and I should have done that from the beginning, sorry that I'm scrambling now, but let me define a coordinate set that I'll call, oh no, let me call it, I will have too many complex coordinates. No, let me just call it, I don't want to introduce too much notation. That's why I'm hesitating. So it's convenient to complexify these 2 coordinates like this, just so that I'm just trying to write one identification. But basically, this identification here will tell you that this combination will be basically periodically identified with R plus over R minus. Yeah. Times 2 pi. Okay? So from the point of view, why am I writing that? It's because now I want to draw it. Here I was drawing still a cylinder, but I shouldn't have drawn a cylinder because now I have 2 identifications. And so I have the identification that tells me that TE is periodic, but now up here in this other kind of angular type coordinate, what the second line is telling me is that I'm gluing these 2 things together. Okay? So the picture, so we have 2 identifications And so basically, instead of drawing a cylinder, I should be drawing that geometry was a torus, was a solid torus, okay? Where one of the identifications, so this is the identification, let me call this identification 1. So this is my cycle. This is the thing that it was a smoothness condition as I went to the origin. So it's a regularity condition of the Euclidean solution. And then this other identification here, let me call this 1, 2, is basically this size of the torus, which is basically the complex structure of the solution. So you can think of this as basically that you have like a square, and you're basically doing identifications that give you the solid torus. Okay? So what we have for BT set is basically the Euclidean BT set. Topologically is a solid torus with complex structure R plus equal to R minus. Sorry. Is there a question? Yeah. Yeah, I was nervous about what was happening there, and what this coordinate transformation told me is that nothing wrong is happening. So it's a smooth point of the geometry. So I went up here, and now I don't have any singularity in the space-time. Let's get now I'm going to compare to global AdS₃. No, it's going to be a torus.
Maybe use this, or otherwise other people.
Thank you. You're trying to characterize the topology of this solution around this point?
No, I haven't made any compromise. I haven't come close to R plus. Like what this coordinate transformation is doing is illustrating that R plus was not a singular point in the geometry. But I'm not going close to R plus.
If you did the same but in any other radius, the analysis will be the same. I mean...
Yeah, the only thing, if you want, R plus is basically the origin here in this Euclidean geometry. But I'm just looking at like, so the first thing that I did, so from the point of view of this line element, okay, you can also do it from the point of view of this line element. You again have to see what happens very close to R plus, and notice that any blow up of the metric components here is an artifact of the coordinates that you use. So usually for general black holes, the metrics are very complicated, and so you can only realize that things were smooth if you kind of zoom in and construct appropriate cross-goal coordinates very close to the horizon. So what I'm doing here, the luxury that I have in AdS₃, these are basically the cross-goal coordinates for the BT set. But I can do it, I don't have to do it in an approximate way, like how you usually do it for Schwarzschild or other type of metrics. Because everything here is like locally AdS₃, I can just write to you, okay, these are the cross-goal coordinates, and just implement it and show you explicitly that there was no singularity, like there's no pathological point from the point of view of these coordinates. And now I just went to Euclidean signature, and I'm inspecting from the Euclidean point of view, what are the requirements for this solution to be regular? That's all I'm doing. But I'm not zooming in like necessarily to any, like of course you can say, okay, this thing, again, it comes because you look at like, oh, you want this thing to not have a conical defect close to the center of the cylinder, right? So in that sense, I went close to the horizon. But in this metric is not close to the horizon. This is the metric in the entire space-time.
Okay, thank you.
Yeah. And
You click the button for 1 second.
How do you know that's the complex structure, and what does that mean geometrically in the solid torus?
it just means like, so a solid, well, okay, it's a solid torus just because the radial direction goes in. But a torus is basically identified. So if you have two coordinates, what I'm doing here, and that's why I built this complex combination to just make it one identification. But a torus is basically a square where you make these two identifications here. And the complex structure is basically how tilted this is.
Ah, yes.
So if tau is purely imaginary, then you just have a square, and you're just doing this. But if tau is complex, then the torus is kind of like you're sort of gluing with a twist. And that's what the complex structure basically accounts for.
Okay, thank you. And how did you find it there in those
Oh,
expressions?
it's basically this. So this part here. So generally, so let me write down maybe one equation that maybe will be a little bit more illuminating for this. So what's convenient to write in this discussion is, so yeah, so usually, so all of this is convenient to package with, like people like to define. So this phi and TE is basically the ones here. So I won't be using the capital ones. The capital ones are a little bit more clunky. And basically what I'm saying, so set, going to set plus 2 pi, and then set, going to set plus 2 pi tau. This is my cycle. So this is 1. And this was, yeah, this was 2. Okay, with tau equal to IL over plus R minus. And here, something else that I should say is that R minus, so this is a complex structure because in this process, R minus is purely imaginary. Otherwise, when you go from the point of view of this line element, if you do the Wick rotation, you get an I here. And if you want the Euclidean geometry to be real, then you have to take R minus to be purely imaginary. Okay, so that's why this is a complex number. So R plus is still real. But R minus is purely imaginary. Okay? Now let's go back to the global AdS picture. Because there's still one more thing that I can say here. So from the point of view, so this was a drawing. So this was the Lorentzian geometry. This was the solid torus was depicting this geometry. When I now go to Euclidean signature, I have the freedom here. So this was time in this picture. So now the Euclidean version of this picture, I can just decide, so I can just grab this torus, right? And I can just decide to make time periodic, right? And I can make it periodic, of course, just straight up, but I can also make it periodic with a twist, right? There's nothing preventing me when I go to Euclidean signature to just like identify it. And so in Euclidean signature, I can basically draw global AdS₃, again, as a solid torus. And I will define a W here that will be phi plus I times Euclidean. And this W will have periodicity 2 pi coming from phi. So which one will be that direction? It will be this one here. So this one will be, let's call it A. Sorry. So this is A. And then, because I identified time with a twist, this is basically this other direction here that I'll call B. And I can do it with any complex number that I want that I'll call tau prime. Okay? It has nothing to do yet with the tau that I defined there. I can just make, this is what we call thermal AdS. You just make the solution periodic with any periodicity that you wish. Okay? Perfectly valid, perfectly smooth Euclidean manifold. But then the question, because it's a question you had, it's like, so what does this, how do I make basically a connection between this torus and this other torus? Okay? So there's a further coordinate transformation that I can do. So this lecture is all about coordinate transformations. So let's see. So those ones there, I'm just trying to decide which, which of all the coordinate transformations I don't want to erase. So let's erase the BTZ metric as written originally. So then let's note that there's another coordinate transformation. Just to go crazy. So if I start from the BT set, again, I'll abuse language. I'll call it rho again. But I hope I don't think it should be confusing. So let me define, so starting from global AdS₃, let me define a tanh of rho squared equal to that. So it looks very similar to this definition. It's basically the same as that definition there. But now this var phi let me do this, okay? So these are, again, these are the coordinates on global AdS₃. And these are the coordinates, basically the claim. This will take me to BTZ. So this is a coordinate transformation that takes me between the two line elements, okay? And what we can do now here is basically say, okay, great. So this is another way how I can see that the two things are basically correlated. So this coordinate transformation, what's doing is basically swapping. That's why you need a complex number there. You need factors of I. So it's kind of swapping t and phi. And what you can see from this beautiful coordinate transformation is that if set, and by set I mean this thing that I had defined here, so if set has this periodicity so if I decide that set has that periodicity like that, then you can go through these steps of what these coordinate transformations mean, and you will get that, sorry, I call it straight omega, or I can't read my, no, I wrote it, yeah, write it like straight omega. Then omega will have that identification. So the relationship between the two geometries is basically a swap of the complex structure to tau to -1/tau. So the difference between those two geometries, it's what's called an S transform. in the complex structure, okay? So basically, Euclidean BT set with tau maps to global AdS₃ with -1/tau. Okay? And what makes a difference when, from the point of view of how we then interpret the solutions in Lorentzian signature is basically which of these two cycles, either A and B or 1 and 2, you decided to open up as you constructed the Lorentzian solution. So in this case, B was the time. And so when you decided to go Lorentzian, you decided to open the torus like this and get a solid cylinder. In the BT set, time is the contractible cycle, is 1. And so you open it like that. And that's going to create a hole in the geometry. And that's why we're going to get a black hole out of it, if you want pictorially. It's not turned on the microphone, but I think.
Does that implies that have two boundaries instead of the?
No, it means like we will have a hole. So if you look at the Penrose diagram, you will be able to keep on navigating throughout.
Okay.
But yeah, but it's basically, from a Euclidean point of view, it's kind of weird. But I just want to illustrate that in this geometry, there's different ways how you can, like from the Euclidean point of view, these geometries are exactly the same. It's just how you decided where you want to put the complex structure. But then there's a difference in Lorentzian signature about like how you open up the geometry. So we'll analyze more the Lorentzian geometry to clarify more what's going on from the Lorentzian point of view.
Would you, in that sense, end up with a solid torus with a puncture?
There's no puncture here.
I know, but what do you mean that you open it? And
When I
so-
go to Lorentzian signature.
Mhm.
So I'll open up, like, it's a bit hard. Sometimes people do like little videos of like what it means to open up that direction. It's easier to see what I mean when I kind of cut the torus like that. But in this case, like you're kind of like opening it and kind of like flips open.
But is it
Yeah.
equivalent to have like a puncture?
There's not going to be any puncture.
Ah, okay.
No, the geometries are completely like well defined.
Ah, okay, so it's like a
They're so
continuous
smooth,
deformation.
yeah, yeah.
Okay, thank you.
Yeah. Very confusing.
Along the
You
same
could.
lines, if I open up horizontally the torus, doesn't it just become a cylinder or not?
Parts of it will look like a cylinder, but you will have a hole here in the middle, which is the size of the horizon. Because this direction here, this is the 2 pi, this enclosed basically, that's why you think of this as like the, like that's why I was calling like you'll get a hole. So this 2 pi basically periodicity is telling you what is the area of the horizon.
Oh, okay, and it doesn't happen with global ideas because,
No, because
you have
it
to
just
open
shrinks.
it in the other
Yeah,
direction.
yeah, I open it in the other direction, and the 2 pi direction just shrinks to 0 size.
Okay.
But in this case, this direction will never shrink to 0 size. It's just the size of the area of the horizon.
Great.
Yeah.
Thank you.
Okay. So this is what's going on from the point of view of these geometries. Now, I also want to illustrate here, perhaps, there's a third thing that you can do. How am I doing on time? Sorry, what time did we start at? What time are we supposed to end? We're finishing at 1? Well, that would be weird if we began at 1 and finish at 1. Sorry. We didn't begin at 11:30, you mean? Okay, okay. Okay. So now, okay, so there's a, so this is, I think this is, it's going, we're going to use this Euclidean properties very soon, but this is basically, from the Euclidean perspective, this is what's happening to this to the solution. So I'm constructing for you, basically trying to characterize these geometries, these BT set geometries, and the punchline is that in Euclidean signature, this is just a solid torus, and it's related to global AdS₃ by taking tau to -1 over tau, okay? But let's return now to the Lorentzian picture.
Sorry, Alejandra, will you come back to this discussion of what it means to open? You were mentioning some things that if you open in one direction, you get a hole. If you open in the other, you don't.
Yeah, well, in that way, I just go at global AdS₃. So if I open it like that, I just get like, you get back here. What I was going to do now was draw the Penrose diagram of the BT set and illustrate more why if I open it in the other direction, I'm not getting back to global AdS₃.
Opening is the same as cutting? Just for me to put
Opening means, like, in the sense of, like, you're not making time, like, you're wick rotating back and not making time periodic. So I'm going back to Lorentzian signature. That's what I meant by opening.
And
So in Lorentzian signature, like, time is not periodic.
Yeah.
That's what I mean by opening.
yeah, so cutting in this direction B is more natural than cutting in A, right?
Yeah,
It's more
yeah.
easy to
But
visualize. How do I visualize cutting in this direction 1?
It's a little bit more difficult to visualize, but, like, you really, like, you kind of, like, flip it up, like.
What can you draw? Like
No,
a
I can't
sequence
draw
of two
it.
pictures?
Like, I can ask for a little video that shows, like, what it means to, like, it's hard to visualize, but, what's that? No, but I know who, like, I know someone that when they give talks, they tell you how to kind of view what it means to open it. Of course, I wrote down for you the line element in Lorentzian signatures to start with, and it just looks like a black hole. So the thing is that always, like, for the black hole, when you go to Euclidean signature, and this is why it's kind of like confusing to understand what's going on, the Euclidean geometry is only illustrating what happens between R plus and infinity. So that's why I'm not seeing, like, the rest of the geometry. So that's why it's kind of, so it's just so you can have, like, an analogy of what's happening. But, like, when you go back to Lorentzian signature, literally what you're doing is, like, it's not cutting this thing and saying, like, oh, now that's your Lorentzian time. It's literally cutting this identification and saying, no, now make this extended up.
But you alluded to a hole showing up.
Yeah, yeah. It's just
What's the hole? Where can I see the hole at least?
Well, this is the hole, right? Like, the torus has a size, and the size is basically the complex structure of the hole. And if you actually compute, like, appropriate holonomies, for instance, in the Chern-Simons formulation, like, if you put a gauge field here and you tell me, like, what are the holonomies around these two different cycles, one of the holonomies is going to be the size of the horizon. So it tells you how, like, big the black hole is. So yeah. So by size, okay, if you want, yeah, it's a complex structure, and that's also, like, when you then go to the Lorentzian picture, this periodicity of 2 pi of phi is not a contractible direction. It never shrinks to 0 size in the, up to R plus, between infinity and R plus, this phi direction that I had here, that I just erased, it never shrinks to 0 size. So that's why I was saying you have a hole, because it's the size of the horizon. So it goes, so this picture is illustrating to you that this thing never shrinks to 0, this cycle number 2, and that's my hole.
Okay, thank you.
So it's like the hole of the donut.
One comment, perhaps. I think it is easier to visualize if you suppress direction number 2, and then if you draw just like a simple plane at fixed direction number 2, you get the eternal black hole from the Maldacena paper, for example. You could open, and then you have the real time. But just to have a picture in mind for Pedro that was asking, it's that picture.
Okay. so now let's continue with properties of this geometry. So I'll go back to Euclidean, sorry, to Lorentzian signature. So I think I was listing, yeah, so I said, so I was in property 1, 2, now let's go to property 3. So these solutions basically are or well, let me put it as BT set is asymptotically AdS₃, meaning that if you grab the line element of BT set and expand it as R goes to infinity, you will get again exactly the same thing that I wrote at the beginning, are asymptotically AdS space times. Okay, so this is to say that you're in the same phase space that I had at the beginning in the previous lecture. So it complies with the same boundary conditions. With the boundary conditions when I was describing the phase space. Okay? And actually something that you can note here is that if you set, no, I'll do this a bit later. Okay. So it's inside of the same phase space. Okay? So now if it's inside of that same phase space, I can compute basically its mass, I can compute the charges that it carries, right? So we had all these like nice definitions of L0 and L0 bar, right? And so what I can do, so let me, look here. So, yeah, let's see in which order. Sorry, I'm going around in my notes. So yeah, so let me, so and it will carry charges. In particular, it will carry charges L0 and L0 bar. And this L0 and L0 bar. Yeah, sorry, let me write it. Okay, let me do this. Sorry, this will be better. So the L plus and L minus, so remember in our phase space, I was defining these like straight L's, right? So you can read off what the straight L's will be in this configuration, and they're going to be this, and now I'll tell you what M and J are in terms of our plus and our minus. So and times J. So you can also write this. This is basically up to coefficients. This is basically our plus over our minus squared. Fill in the coefficients that you have there. And then these charges here, that I have the calligraphic L's, are basically going to be 1/2 of ML plus J and 1/2 of ML minus J. And this basically justifies the notation of why I call one symbol M and the other symbol J. And it's because the mass is the sum of these two charges, and the angular momentum is the difference between these two charges. So hence, M is mass, and J is angular momentum. Okay? And this is just because L0 was the charge, sorry. So L0 plus L0 bar is the charge associated to dt, and L0 minus L0 bar is the charge associated with d phi. And dt and d phi are killing vectors of the BTZ black hole. No, so now I'm in Lorentzian. So now everything is real. So we went back to Lorentzian, and because charges are always computed in Lorentzian signature, just because I like my time to describe a Hamiltonian time evolution. So yeah. So charges, of course, some people like to compute charges in Euclidean. I get nervous, but yeah, this is a Lorentzian computation. R plus and R minus, again, are real parameters. So yeah, so if you go to Euclidean signature, and this is very common for rotating black holes, even in higher dimensions, that if you go to Euclidean signature, you have to Wick rotate the angular momentum, if you've ever encountered that. So I could also have said, like, oh, when I go to Euclidean BTZ, J has to be purely imaginary. Yeah, yeah, so they're the equivalent statements because of this relationship. So Wick rotating, like considering purely imaginary J is the same as saying, oh, you're considering purely imaginary R minus. Okay, so that ties it with a discussion that we had before. And also note, there's so many things to note about this geometry, that from this point of view, now with this notation, global AdS₃ is basically the solution with M equal to, I should know this by heart, and J equal to 0. Okay? So if you just take these values in the BTZ metric, so you put here J equal to 0, so R minus is 0, and then M to be a negative number, which is that minus 1/8, which will make R plus be purely imaginary, you'll see that the line element becomes global AdS₃ written in the first way that I wrote it before. So this basically makes these choices. So just to convince you, we had these blackening factors in the BTZ metric. If you make these choices here, what's happening is that this is just becoming if I had my units correct, it will just become that, which is, you remember previous lecture, the first time I wrote global AdS₃, it had this. So that's just basically the choices that make that happen. Okay? So it looks like a black hole with negative mass. So now this is interesting, because now from this Lorentzian perspective, the BTZ solution has some mass and some angular momentum determined by R plus and R minus. And global AdS₃ has a very specific value of mass and angular momentum. So from the Lorentzian point of view, this is already indicating to me that they're not the same solution. So in Euclidean signature, they look like the solid torus, where you took tau to -1/tau. But in Lorentzian signature, there are clearly states that I will describe with different energies. Okay? And we'll understand what that means. It will have a very, very nice meaning very soon, hopefully by I think next lecture I'll tell you more about what that means. So the fifth point here is that these solutions, so okay, I think from this point of view, it's already compelling to say that this solution, the BTZ solution, is not the same. So we're getting the idea that at least in Lorentzian signature, global AdS₃ is not the same as the BTZ. They carry different set of charges, these two solutions. And actually, the BTZ solution has horizons. So globally, let's look, for instance, at this type of transformations here. So when I was going and telling you, making these statements that these solutions were basically locally equivalent. So did I go too fast? Is there something here that I'm being sort of, no, I didn't go too fast? There's no subtlety? Robins.
Poincaré patch in 4D. The idea is that in Lorentzian signature is a patch of the global AdS₃, but when you go to the Euclidean signature, they were the same. However, here, because we are in 3D, the Poincaré patch has 0 mass. So there's
yeah,
and
Poincaré in these conventions, yeah, has 0 mass.
So there is a distinction between Poincaré patch and global AdS.
Yes.
And
you do have to be careful that they're, strictly speaking, yeah, there's an interpretation for that, and it's something special to do to these CFTs of like how you get this Casimir energy.
But, yeah, I understand that point, but at the level of like thermal physics, Poincaré patch doesn't play any role.
You can also relate. I can also go to the Poincaré patch, but I'm running short on time, and I had like that equation there, but like. Yeah, from the point of view of the CFT, the only thing, it's like basically going from the cylinder to the plane. So you can understand from the point of view of the bulk, like the coordinate transformation that makes you go from global AdS₃ to the Poincaré patch is equivalent as going, yeah, from the point of view of the boundary metric, you're going from the cylinder boundary to the R2 boundary. And that changes, even in the CFT, that changes the notion of energy because it's there's a Casimir energy associated to that transformation. So I don't want to write from this point of view, so right now here my boundary is a cylinder. So technically speaking, it does not include Poincaré because Poincaré does not have like an identification in phi. So I do have to do a conformal mapping to get to it. If you insist on evaluating the energy for like the Poincaré solution with phi periodic, it's what's called like a small black hole. It's like the mass equal to 0 BTZ black hole because phi is still periodic. So there's a little subtlety there. Yeah, yeah, yeah. You can also talk about like planar BTZs. They're not like you do have to be a bit careful. Like, but it's basically planar BTZ is like going to a Rindler observer. So it's not quite a thermal state in the same way. It's more like going to like just carving up like some part of like the Poincaré solution. Yeah.
In this language, do you have any meaning for things with M negative but higher than this? Higher than the...
like lower, like higher in magnitude? Oh, there's nothing else. There's nothing in between. So if you draw like the set of regular solutions, So let me turn off angular momentum just because I'm lazy. But like, so if you plot like the set of masses and what are regular masses, so here you have like the -1/8, and here you have 0, and this is BT set, but there's a gap in the spectrum. Even classically, yeah. Well, the only thing that you can have here classically are the boundary gravitons. But there's no like smooth solution. So you can add like little wiggles. You can add the perturbative states, but there's no like regular like solution between 0 and -1/8. So this is what we call like this mass gap condition in AdS₃. So the first like big states come from 0 and above. If you add angular momentum, then it looks like it will look like a little like thing opening like that. But yeah, so you do have like so when you embed this in higher dimensions and you consider solutions like, so like let's say, since you like string theory, so like if you're in like type 2b supergravity and you consider solutions that have an AdS₃ factor, there are regular solutions from a higher dimensional point of view that live in between here. If you compactify them from the point of view of AdS₃, they look like conical defects. But from a higher dimensional point of view, the extra dimensions kind of regularize those cones because you have other identifications. And they're basically, like, some of them will look like just more interesting quotients that you can have in higher dimensions. Some of them will be like these fuzzball type geometries. So if you have more dimensions, then you can populate more what happens here. But if you just have pure gravity and nothing else, there's no other fields, there's no other dimensions, then there's nothing in between. So pure gravity has this spectrum. But if you have more stuff, then you can populate that.
What is the physical interpretation of having the pure gravity have a negative mass? And is it related to the fact that this is a space with negative cosmological constant?
Don't stress too much. Like, no, it's not too important that I know it looks ugly to write down negative here. This is just a convention. What's important in physics is that Hamiltonians are bounded from below.
Yes.
So what I don't want is to have infinitely many things that are negative down here. So where I put the 0 is a choice. I could have shifted all of my charges such that this guy was the thing with mass equal to 0. And then in my definition of charges, then I would have added here like a thing. So what's important is that this is the lowest configuration, but not that, it's just where you put the reference energy.
But then what does it mean that there is a gap in the spectrum? Why can't I have something?
Because gravity is difficult.
Okay.
Yeah, in higher dimensions, this doesn't happen. You can have,
Thank you.
It's really, it creates like a really big pain because, I'll tell you about this in the last lecture. This is what makes AdS₃ quantum gravity really difficult.
Thank you.
It's this large gap.
Yeah, actually, I thought that in CFT shouldn't be any gap.
No, you always have, the energies are always quantized.
Yeah.
No?
Yeah, that's,
Yeah.
but, so
No, like, well, in a CFT, what happens if we're getting ahead of ourselves because we haven't done AdS₃ yet. But sure, this will be the vacuum state, and then you can have some other, but there's always going to be in a compact CFT, in something that has discretized energy eigenvalues, there will be an energy separation between every state that you have in the theory. That's what makes it quantum. So yeah, so these gaps, this little like steps between things, sometimes they're really small, sometimes they're bigger. In this case, yeah, I have a big one. It's controlled by G Newton. Yeah. But there's always gaps. Like, it's just that in gravity, they tend to be big. But that's all. But like the boundary gravitons are also like, their energies are modded by this integer n. And they have energy differences between them, and that's perfectly fine. Of course, you take thermodynamic limits, and then things look continuous, but in the quantum theory, everything is discretized. So in a CFT₂, it's also, there's a discrete spectrum, and yeah. Yeah, what's remarked, like, yeah, I don't want to, because I haven't gotten to the CFT yet, so we haven't tried to understand this, but this is just a discussion of like, okay, what are regular solutions with some set of boundary conditions, and that's what we're looking at. Okay, shall we continue? Okay. Okay, so what sorry, I lost my line of thought. Yeah, so this thing has a horizon. So, yeah, so what I wanted to say was that, so there exists an outer horizon for this geometry. So as I mentioned, this thing had like 2 killing vectors. dt and d phi. And you can construct a combination of these 2 killing vectors. Like this, okay? So where that omega h is the ratio of r minus on r plus, and it satisfies. Oh yeah, we were talking about the coordinate transformation. Okay, sorry, that's what I was going to say. So this thing, the norm of this killing vector is always positive if r is equal to r plus, and the norm of this vector is exactly equal to 0, and r equal to r plus. Right. And it would also satisfy, it's a killing vector that also generates a killing horizon, because it will satisfy this beautiful equation which defines the surface gravity, kappa plus, in terms of that. And this combination we've seen not so long ago when I was talking about beta. Okay? But yeah, sorry, I lost my line of thought. So, because we were saying that global AdS₃ is different from BTZ, and how was that, what was the thing that I went through too quickly when we were doing this exercise? But all of you were very happy with my coordinate transformation. So what am I overlooking here? Because now I even now constructed a killing vector that becomes null. So there's clearly a definition of a horizon in this geometry. So where are we being sloppy? So the point that I'm being sloppy about, and where I go fast, is that this coordinate transformation is not defined everywhere. In particular, it will become singular when r is equal to r plus. So what I'm doing is actually relating BTZ to global AdS₃ by patches. It's not a global identification of what's going on. It's basically a patch by patch realization of how locally BTZ looks like global AdS₃. So let me draw from that point of view, given that now we have realized that there was an outer horizon at r plus. So what's going on from the point of view of the Penrose diagram is that the solution, let me just draw it. Yeah. Let me draw it like this. So what's happening here, so in this Penrose diagram, this line here, so this is my boundary where R goes to infinity. Okay, so let's say we started with a geometry out here when I wrote down the metric where I reach infinity. And this horizon is this diagonal line, so this is R equal to R plus, what we call H plus, is this line here. And these coordinate transformations, so this beautiful transformations that I wrote, there was a tangent here as well. Tangent hyperbolic of rho equal to the R plus. So this coordinate transformation is actually only valid inside of this patch. So what I did from the Lorentzian point of view was to tell you how this patch was locally related to global AdS₃. But the coordinate transformation breaks when I get to R equal to R plus. Of course, the geometry from the Lorentzian point of view clearly continues. And so then when I go between this surface, I have to then reconstruct, I can construct another coordinate transformation. I can have another chart that will tell me, how then this solution is related to global AdS₃ again. But you do it patch by patch. So locally, you can always kind of relate to global AdS₃, but there's not a single globally well-defined coordinate transformation that tells me that the two solutions are the same. Okay? So this thing here, so when we were going through this, we were just looking at this patch of the geometry. And here again, I have a R equal to R plus on this solution. And when we were doing the Euclidean analysis, this is the portion that I was going into Euclidean signature. Okay? The solid torus is basically taking this patch of the geometry to Euclidean signature, and then we were seeing that the two solutions were related. Okay? But now in Lorentzian, you get to R plus, there's no problem. You can continue the geometry further down, and then you will hit R minus. So you will have an inner horizon. And then you can escape again out to infinity, and then you will have another R minus, and the thing keeps on repeating up and up and up. So the Penrose diagram of the BT set is something that has horizons inside of it, in contrast to the Penrose diagram of global AdS₃, which is just square.
Why is it the lower part not R minus 2?
This one? No, because you have the horizon. No, this. No, it's R plus on both directions. R minus comes up here. This point is the bifurcation point, and it has to be regular. Okay. And then I think, I'm done. It's 1 o'clock. So then I think what I'll continue tomorrow, I'll tell you more. I haven't finished telling you all the things that we need to know about BT set, but I hope I have been convincing you enough that this solution, it's within our phase space. It's a regular solution. So there's absolutely no problem with it, but it's not equivalent to the global AdS₃ solution. And there's still a large diffeomorphism, so this is also something that you can call a large diffeo that tells you how by acting, so the way that you can think about this is that if you start with global AdS₃, you can create via a large diffeomorphism a black hole. And this large diffeomorphism, basically, if you started with a solution that had this energy, you will end up with a solution that has this energy. So it's a non-trivial diffeomorphism that acts non-trivially on the boundary from that point of view, okay? So it's not infinitesimal. So again, these are large transformations in the sense that they're changing. They're non-perturbative in the sense that they're changing the topology of what's happening in the space-time. So they're different from the boundary gravitons. That's why we call them non-perturbative instead of perturbative. And they have this effect of basically creating horizons. Okay? So I think, yeah, I'm done for today. Tomorrow we'll keep on talking. There's still a few more things that I need to say about BTZ before we move on to quantum things. So, thanks. All right.
Okay. Yes.
Okay. Thank you for the lecture. So I was wondering, can I see the fact that you said that you cannot shrink when you decompactify, like the torus, you go to the Lorentzian signature, you have a hole in the BTZ black hole. Can I see that by the fact that if I take the complex structure here to 0, that would mean that I would take the complex structure of the BTZ black hole to infinity?
No, it's just the radial direction. So sorry, I erased the BTZ line element. So here, this guy has periodicity 2 pi. Yeah. But the size is the fact that I'm saying that something shrinks to 0 is because I have this cinch in front. So this cinch goes from being like very big and infinite up to 0 when rho is equal to 0. So that's why I drew it as like, oh, it's something that can shrink to 0 size. In the BTZ, so when I write down in the BTZ line element, there were many things. When I go to R+, the size of the phi circle is multiplied by R squared. So when I'm at R equal to R+, which was the origin, so R equal to R+ is when rho is equal to 0. This thing does not shrink to 0. R is equal to just R+. So that has a finite size. So that's why I said like there's a hole.
Okay, but I cannot see that with the complex structure, the tau, it's a tau there?
Tau just tells you like what size is this. But it has nothing to do, in this picture, tau is just telling you how you decided to identify time.
Okay, but if I take this to 0, that means that I'm not identifying
You're
time.
making the,
if I take this
yeah,
to
you're
0.
making it very like thin. Sorry, to 0 or to infinity?
I'm thinking about 0, because if I take this to 0, that would mean that I'm taking the other tau to infinity. That means that R+ is 0.
Ah, okay, sure. Yeah. But yeah, it's kind of a singular limit of the torus, but yeah, that you're kind of, no, yeah, you're just making it like very thin.
But they both coincide, right? If I take R+ to 0.
Yeah, but it's kind of yeah, it's just that in Euclidean signature, yes, but in Lorentzian signature, you have to be careful. Because in Lorentzian signature, there's no such equivalent statement. In Lorentzian signature, this tau prime here disappears from the global AdS₃.
Yeah, sure.
Right? So when I go to the Lorentzian signature here, I don't know, what are you telling me that tau prime is going to 0? There's no, like, there was this time and a period phi. So the games that you're playing are just like Euclidean games.
Okay.
So that's why Euclidean quantum gravity is also a little bit subtle, because when you want to identify states and distinguishable physical configurations, that for me it's a Lorentzian definition, not a Euclidean definition. But the Euclidean signature is going to be super useful for us to manage to do some computations and to get some physics out of it. So that's also why I was stressing how they're related in Euclidean signature. But clearly, like if you wanted to understand a Hilbert space, the Euclidean picture does not give you a Hilbert space understanding of what's going on. It does not give you a phase space. It just tells you there's this interesting topologies, and this is how you characterize these topologies. That's what it's doing at the moment.
Okay, thank you.
Okay, we have time for one more question, perhaps? Yes. Okay,
No, but
Pedro plus one.
Just a quick question. So if I add matter, how does it work compared to higher dimensions? In higher D, if I throw a shell of matter, for example, if it's big enough, it forms a black hole. How does it work in 3D if I send shells of matter?
You can do that. You can throw in shells of matter. There's various papers that did that. But it's always very kind of like non-perturbative how you create the black hole. But people it would also intuitively work, but it depends on like
Physically, what happens in 3D gravity? If I throw matter, do I form black holes or not?
Yes, you would. Yeah. Yeah, but like if you ask me like, oh, can you write like a system where you track everything down? It's a bit tricky, but because gravity is like it's topological as well, right? So the transition between like being like a star and then being a black hole is something that is a bit more subtle to describe. But you can, like there's papers I'm thinking right now, papers of Julian Sonner with Tarek Anas and Tom Hartman from a few years back that they were trying to describe gravitational collapse in 3D by having appropriate matter and then like trying to see it collapse and then give that like some CFT description. But there's always like approximations or assumptions that you have to do at some point. There's always going to be something violent of like how you create the BT set.
That last step is worse in 3D compared to 4D?
Yeah, yeah.
Would it be right to say that what we've seen here is that what allows you to justify why Schwarzschild solution is not the Rindler wedge, it's not the Rindler patch in Minkowski, because the wild tensor is not 0? Because this picture is very similar to the Rindler when you start in Minkowski and you go to the Rindler patch, you do these same drawings, except that you don't have all the up.
No, but it's a different drawing, right? Like the Rindler patch in Minkowski, you mean like that you draw this, and it's like the guy that like traces out like one part?
Yes, but that's not the Schwarzschild solution because you don't have that the well tensor is 0 there. And here,
no, but okay, there's no singularity. So right, so this black hole, that's why I also didn't draw like a little like curly line. So usually in higher dimensions, if I was doing this for Kerr, like you would have drawn like here, like, there's a singularity, and you hit the singularity in a time-like fashion, right? So in flat space, you have this thing here. But this is not a Rindler horizon because it's not observer dependent. So in the planar case that Robinson was asking me, if I don't make phi identified periodically, then I would not have drawn this, then it would have been, I would have drawn something more equivalent to like, oh, you're just picking like some coordinate patch of global AdS₃ or Poincaré, and it's an observer-dependent statement. This H plus is not an observer-dependent statement.
Okay.
So that's why it's a proper horizon of the geometry. But in the Rindler case, these are basically observer-dependent horizons because of a choice of coordinates that you made. In the black hole, this is not a choice of coordinates. These, if you want, these properties of this killing vector are not dependent. Like the fact that psi squared is equal to 0 at a point is not a coordinate dependent statement.
Okay, thank you.
Okay, so we thank Ale again.